Good afternoon. I am Professor Gary Bernstein from the University of Notre Dame Department of Electrical Engineering, and I teach a course in an introduction to electrical engineering. And in this course, I cover a variety of topics, many different things from semiconductors to light bulbs, and including communications and some systems concepts. So the purpose of today's video is to provide a very brief and simple introduction to time domain and frequency domain and the relationship between the two. And I have put together a demonstration for using a bell, which is intended to show what I think is a difficult concept. Basically, it's resonance, but also an impulse function or a delta function. So I'm going to start by showing some slides which I low-tech drew on a piece of paper, and it's going to explain time domain and frequency domain and Fourier spectra, and then I'm going to give a short demonstration regarding this bell and the fact that an impulse has a frequency spectrum which contains all frequencies, basically. So we're going to go over to here, these slides. I'm going to talk my way through these slides over the next several minutes, and then I'll switch to the demonstration. So when we talk about time domain, what we really mean is the kind of thing that you expect from a function, just how it changes in time. So you recognize this as a sine wave. It has a period that I call t0. Now this is a pure sine wave. In other words, it's a perfect sine wave. And it has a frequency, which is 1 over the period, t0, 1 over the period. Now we can speak of frequency as either cycles per second or radians per second. So one circle has 2 pi radians. So one cycle of anything has 2 pi radians. So if we do a certain number of cycles per second, we do 2 pi times that in radians per second. Excuse me. So we often write sine of omega t equals sine of 2 pi ft, depending on whether we represent the frequency in hertz or cycles per second, or we represent it in radians per second. Omega is 2 pi times the frequency. Now any sine wave has an amplitude A, so I indicate it here. So this is a graph of the amplitude of the sine wave as a function of time. And again, it's a perfect sine wave. There's nothing else there other than just the sine wave. Now, if I want to represent that in the frequency domain, where all I want to communicate is how much is there of a particular frequency, you would say, well, of course, there's only one frequency there. It's a sine wave, and it had a frequency of omega naught, or f naught, depending on if we're in radians or cycles per second or hertz. And when we draw a plot of how much of every frequency is there, we call that the Fourier spectrum. So in the frequency domain, we say we only have some of that one frequency and no other frequency. So the Fourier spectrum of a sine wave is a delta function. It's a sharp value only at that frequency. It's a single frequency. So the plot of the frequency of how much of each frequency there is as a function of frequency is this delta function, because there's only one frequency in the signal that I'm analyzing. So that is the time domain in time, and this is the frequency domain in frequency. I'll show several examples now. Let's ask, what is the frequency spectrum of something really simple? A battery. A battery has a DC voltage, VDC. So in time, what is the output voltage of the battery? Well, it's constant. It's just the battery voltage, which I call VDC. So this is a simple DC voltage. Again, this is time, and this is a plot of the output voltage as a function of time, and it doesn't change. As time marches on, the voltage is the same, the same, the same, the same. Now, if we did this for years, it would drop as the battery got older and weaker, but this is only a few seconds, so this plot is a constant. So what we're doing is we're showing the time domain here for just a simple DC voltage, and in the frequency domain, it's actually quite simple. It's a delta function at 0 hertz. It has no frequency, it is DC, but it does exist in the frequency domain as a delta function at 0 hertz. So we draw it as a delta function, and the height of that delta function is VDC. So now I've given you two examples. I've given you a sine wave of amplitude A, whose frequency spectrum is a delta function at the frequency with amplitude A. I've shown you a battery that's a constant in time, whose output voltage is VDC, and its frequency spectrum is a delta function at 0 hertz. We're going to get a little more complicated now. What if I take that sine wave and I add to it a DC voltage? I could do that with a sine wave generator in series with a battery, for example. Or I could just write it as VDC plus sine of omega naught t. So in time, it is the sine wave, but it's raised up by the DC voltage. So I have two components now, a DC component and a frequency component at omega naught. And by the way, I just want to say that sometimes I say omega, sometimes I say F. The concept does not change its frequency, just whether or not it's expressed as radians or hertz. It's not much consequence. So here's the sine wave, but it's been raised up compared to the sine wave that I started with that was around 0. Okay? What is the frequency spectrum of this new wave? And the answer is it has two frequency components. The sine wave, just like it was at omega naught with an amplitude A, and the DC component that was added to it. So if I look at this in the frequency domain, I see a level shifted sine wave is represented by the DC component plus the fundamental component of the sine wave, or the frequency component of the sine wave. Now we're going to get a little more complicated. What if we add two frequencies together? Sine of omega naught t plus sine of omega 1 t. Now you could think of that as a piccolo playing a note while a tuba is playing a note, presuming that the piccolo has only one frequency at its output and the tuba has only one frequency at its output. Now I don't think a tuba can play any note as high as the lowest note on a piccolo, so we'll assume that the lowest frequency here is the tuba and the highest frequency is the piccolo. If we look at that in the time domain, just the sound that we were to hear, it would be a high frequency and a low frequency at the same time. Moving air is what causes sound. The air can only be at one place at one time. So if we plotted the position of the air, or likewise the force on a microphone, or likewise the voltage out of a microphone as a function of time, it would be the piccolo with its high frequency riding on top of the tuba at its low frequency. So we have a period t naught for the tuba, we have a period t1 for the piccolo, we have a frequency omega 1, which is 1 over t1 for the piccolo, and we have a frequency, I wrote f naught, I'm sorry, 1 over t naught. This should be f1. I'll fix this on the fly. F in hertz is the reciprocal of time. So we have 1 over t naught equals f naught is the frequency, f naught is the frequency of the tuba, f1 is the frequency of the piccolo. So we have a high note doing this, and a low note doing this. What does the frequency spectrum of that look like? Well, I think you can guess. It would be a peak at the tuba frequency and another peak at the piccolo frequency. I drew the piccolo frequency smaller, amplitude smaller, higher frequency for the piccolo, lower frequency for the tuba, higher amplitude for the tuba, lower amplitude for the piccolo. I drew it that way because of the way that I imagine the amplitude of the piccolo. We'll just say the piccolo is playing quietly and the tuba is loud. So there it is. Those two frequency components together have a frequency spectrum that contains those two frequencies. Now we get to a square wave. A square wave is more complicated and has much more spectral content, many frequencies. So something that's flat and high and then zero and high again and zero and high again, that's called a square wave. There's something called the duty cycle, which is the fraction it's on to the period. So it's T on over T naught. So this would be like a duty cycle of about 25%, let's say. And the fundamental frequency is 1 over T naught, or F naught. So now, does this have a frequency component spectrum? Of course, and it's much more complicated than anything we've seen yet. The frequency spectrum of a square wave has the form of sine of x over x. That's called a sinc function. Put another way, it's 1 over x times the sine of x. Now we know that the sine of x looks like that. 1 over x looks like this. So sine of x over x looks like a decaying sine wave that drops off like 1 over x. Now in the case of our square wave that has some fundamental frequency f naught, we have what are called harmonics. I should write down the word harmonics. The fundamental frequency is called the first harmonic, and then there's multiples of 2 omega, so that'd be omega naught, and then we have another component at 2 omega naught, a component in 3 omega naught, 4, 5, 6, 7, 8, to infinity. That means that we would need to have sine waves at all of these frequencies, essentially going out to infinity, that if we added them all up again together, we could reproduce this exactly. Rarely in a real system do you get, well, never do you get infinite frequency bandwidth, but sometimes it can be very wide and you can reproduce the square wave pretty accurately. So again, the frequency spectrum can be thought of as what frequencies do I need and how much of each to add up to create the original waveform. In this case, it's a sinc function as an envelope, and then we only have the components which are at the fundamental, the second harmonic, third harmonic, fourth harmonic, fifth, sixth, seventh, eighth, and so on, and they drop off until they become insignificant. But without these high frequency harmonics, we cannot get the sharp edges of the square wave. They'd be rounded. That's getting into too much detail. I'm getting to a point in just another couple of slides, another few slides. All right, now a special case of the square wave is a 50% duty cycle square wave. This is rather interesting, I think. So if we imagine a square wave with a 50% duty cycle, it has a frequency spectrum that's kind of interesting. It would have a DC component that I don't have drawn here. It would have a fundamental frequency at omega naught, but the 2 omega frequency would fall right at the frequency at which it crosses 0. Then it comes back up in amplitude at 3 omega naught at the peak, and at 4 omega naught it's 0 again, and then 5 omega naught is the peak, and then 7 omega naught is the peak. So interestingly, I think interestingly, this waveform has the following frequency spectrum. There are only odd harmonics at omega naught, 3 omega naught, 5 omega naught, 7 omega naught, and the amplitudes of those drop off as 1 over omega naught because the entire spectrum drops off at 1 over omega naught. So if you only looked at these dropping off as 1 over omega naught and the odd harmonics, it would look nothing like a generalized frequency spectrum of a square wave, which can be very complicated. But at the 50% duty cycle, things move right to the middles and at the cusps where they go to 0. So what is the overall point I'm trying to make? The overall point I'm trying to make is that a complicated wave has a complicated frequency spectrum. A complicated wave has a complicated frequency spectrum that contains many, many harmonic components, many frequency components. And you can't get your wave back unless you add up many, many, many frequency components to reconstruct or synthesize the original wave. Now we're getting much closer to the bell. What am I going to say about this bell that I have here? I want to tell you about one more frequency spectrum, and that is a delta function in the time domain. What is a delta function in the time domain? Well, here it is. That was a delta function in the time domain. It's also called an impulse function. We draw the delta function as a peak at 0 time, and it's like a sharp hit with a hammer or a bolt of lightning. It's sharp and it's short. What's the spectrum of that? In fact, if you wanted to reconstruct a really good delta function or a perfect delta function, you would need every possible frequency with the same amplitude going out to infinity. Another way to say that is that a delta function contains all frequencies with equal amplitude. I could have said that this square wave contains all of these frequency components. Well, a delta function contains all frequencies at equal amplitude. So, I want to try to demonstrate that in some way which can make it real to you. So I have a bell here. Here's a bell. And a bell has a clapper. See the clapper here? Right, what does a clapper do? It rings the bell. You may have never thought of ringing a bell this way, but a clapper rings a bell. What just happened? I'll tell you what just happened. I gave the bell an impulse. I input to the bell a delta function. It was short, it was hard, and that short rap with this piece of metal, the clapper, it didn't end up with every possible frequency. I don't hear really low notes. I don't hear super high notes. I only hear this frequency that the bell is ringing at. It's a little complicated, but it's just basically one frequency in there. There are more than one frequency. What is happening is a phenomenon called resonance. And in resonance, something will vibrate at its own choice of frequency. And the bell is choosing that frequency to vibrate at. Even though I gave it every possible frequency, because I know that a delta function is all frequencies, it chose to resonate at the frequency that we're hearing. All other frequencies die out. The resonant frequency lives. I just want to show you something. If I hold the bell, it's not going to ring at all because I'm damping every frequency. So let me put this into better terms, different terms. So I'm going to try to get a frequency spectrum analyzer here by handing it to my assistant. So Sam is back with the camera and show this. This is a frequency spectrum analyzer. There are many of them available for free for Android phones anyway. And this goes out to 10 kilohertz. I think I need to zoom in a little bit more. Now it goes out to 1 kilohertz. Let's zoom back a little bit. So this is the frequency spectrum of my voice. If I whistle, there's a peak there. You can see the spectrum changing. See that? Now when I ring the bell, we're going to see all the frequency spectra, all the frequency components that are resonant in the bell. And there they are. Oop, I ruined it. Here we go. And as it dies out, they go away. Now watch what happens if I do this. They went away immediately. So the microphone is picking up all the frequencies and displaying them on this. Good. What I want to really demonstrate is the resonance that the bell only responds to the resonant frequencies even if we give it other frequencies. Now, I hope this comes out well on the microphone, on the phone. We are limited here in resources. I'm going to plug in an amplifier. It's a tiny little amplifier. And I'm connecting it to a speaker. Can you zoom in on this, please? This is a speaker that I took a razor blade and I cut out all the paper because I want to excite the bell through this putty on top of the bell. I don't want to hear the speaker itself. I just want the vibrations of the speaker. It's vibrating. I want the vibrations of the speaker to excite the bell, but I don't want to hear it. Unfortunately, it's not perfect, and we can still hear it. So I know that the resonant frequency of that peak that you saw is 577.9 hertz. So I'm going to show you what happens if we create an output below 577.9. We're at 575.4 hertz, and I'm going to increase it, and I'll be quiet. But when we get to the resonant frequency, you should hear the bell ringing, and I'll prove that it's ringing by touching it with my hand, and you'll hear it stop ringing, even though this gets in the way, which is really unfortunate. So we're at 575.4 hertz. It's such a good resonator that we have to change it only by 1/10 of a hertz. It's that accurate, the resonance. So notice as I grab the bell, there's hardly any difference in sound. We're not exciting much. I'm increasing the frequency. 576, not much is happening. 577.1, 3, 5, 7. It got a lot louder. See that? The bell's really ringing now. The way to interpret this is that when there's a delta function, I put in all frequencies, including the resonant frequency. So you see, that's almost the frequency that should be about the same frequency, exactly the same frequency that we're hearing it resonate at. Let me go to slightly different frequencies. So we're at 578.1, 2, and by the time we get to 579, I hope this can be heard on the microphone, the resonance is basically gone. So what's the lesson here? It's about resonance, that the bell wants to resonate, but the fact is, on this graph right here, if you could show this, all frequencies are represented by the clapper, but only in this range of frequencies here, where this is about 577.9 hertz, does it really want to use that frequency component that came in from the clapper? See, that is the resonant frequency. Well, let's get back to 577.9. So there it is again. 577.9, it's resonating, and it's not, and it's resonating. Okay, I'll stop in just a few seconds. So the message is that waveforms, still ringing, and it stopped. Okay, waveforms have frequency content. That frequency content is displayed in the frequency domain. We talk about it, we call it the Fourier spectrum. Complicated functions have complicated frequency spectra, and a delta function contains all frequencies equally, and to prove that, I related the result of a clapper, which is a delta function, to discrete frequencies, and showed that the bell responds only to one particular frequency, which was there when I clanged it with the clapper. So, if you could, all right, I hope that was understandable. That was about 30 minutes, longer than I expected, but there was a lot to say. So, thank you very much for your attention. Oh no, now it's recording a second one. My mistake.